Welcome to this lesson on metal organic frameworks, or MOFs. These are some of the most remarkable nanomaterials we've ever created, with surface areas that can exceed that of an entire football field in just 1 gram of material. So what exactly are metal organic frameworks? Let me explain their structure and why they're so special. MOFs are porous crystalline materials constructed from 2 main components working together. The first component consists of metal ions, or metal clusters, that act as nodes in the structure. The second component is organic linker molecules, which are like struts or bridges connecting the metal nodes. Imagine a 3-dimensional network where metal nodes are connected by organic linker molecules, creating a scaffold with large empty spaces inside. These empty spaces are what give MOFs their incredible properties. The resulting structure creates enormous internal pore space, kind of like a molecular sponge with cavities throughout. But why do we care so much about surface area? Let me explain why this property is so critical. Surface area determines how much of the material can interact with gases or molecules. The more surface area, the more interactions can occur. For applications like gas storage, catalysis, and separation, we need to maximize these surface interactions. That's where MOFs excel. Let's explore this famous football field analogy that scientists use to describe MOFs. A standard American football field, including the end zones, has an area of about 7,140 square meters. Remarkably, some MOFs have specific surface areas exceeding 7,000 square meters per gram. That means 1 gram has the surface area of an entire football field. Here's the visualization. This entire football field, all 7,000 square meters of it, is equivalent to the internal surface area contained in just 1 gram of certain MOF materials. It's absolutely mind-boggling. You might be wondering, how is this even possible? How can something so small have such a large surface area? Let me explain the mathematics behind this. The key concept here is specific surface area, which is surface area per unit mass. Specific surface area equals total surface area divided by mass. This is measured in square meters per gram. For MOFs, typical values range from 1,000 to 10,000 square meters per gram. Some exceptional MOFs exceed this range. One of the record holders is MOF 210, with a specific surface area of 6,240 square meters per gram. Another impressive example is NU 110, with 7,140 square meters per gram, literally matching a football field. Let me walk you through a numerical example to show you how we calculate and understand these surface areas. Let's consider a simple cubic pore with dimensions of 2 nanometers on each side. This is typical for MOF pores. The volume of this pore is 2 nanometers cubed, which equals 8 times 10 to the negative 27 cubic meters. The internal surface area of this cubic pore is 6 times the area of one face, which gives us 2.4 times 10 to the negative 17 square meters. Now let's assume our MOF has a relatively low density of 0.5 grams per cc, which is typical because they're so porous. Let's also assume that 80% of the total volume is empty pore space, which is reasonable for highly porous MOFs. The number of pores equals 0.8 times the total volume divided by the volume per pore. For 1 gram of material with these assumptions, let me calculate the total surface area. The total volume for 1 gram is 1 divided by 0.5, which is 2 cubic centimeters, or 2 times 10 to the negative 6 cubic meters. The number of pores is approximately 2 times 10 to the 20th pores. That's 200 quintillion individual pores in just 1 gram. The total surface area is the number of pores times the surface area per pore, which gives us approximately 4,800 square meters. That's more than half a football field from our simple calculation. So what makes MOFs special compared to other porous materials? Why do they achieve such extraordinary surface areas? First, MOFs have extremely low densities because of their high porosity. Some MOFs are more than 90% empty space. Second, the pore sizes are in the nanometer range, which means you can pack an enormous number of these tiny pores into a small volume. Third, the regular crystalline structure maximizes packing efficiency. Unlike random porous materials, MOFs have ordered, repeating structures. Fourth, Scientists can tune the pore sizes through careful synthetic control, optimizing for specific applications. Let's compare MOFs with other porous materials to appreciate just how special they are. Activated carbon, which is widely used for filtration and adsorption, typically has surface areas from 1,000 to 3,000 square meters per gram. Zeolites, which are naturally occurring or synthetic aluminosilicates, have surface areas from 300 to 900 square meters per gram. Silica gel, commonly used as a desiccant, has surface areas from 200 to 800 square meters per gram. MOFs surpass all of these, with surface areas from 1,000 to over 10,000 square meters per gram. They represent a quantum leap in porous material technology. You might ask, how do scientists actually measure these enormous surface areas? The answer is the BET equation. BET stands for Brunauer, Emmett, and Teller, the scientists who developed this method in the 1930s. The BET equation relates pressure P to the volume 5 of gas adsorbed. P0 is the saturation pressure, Vm is the monolayer volume, and C is a constant related to adsorption energy. The standard method uses nitrogen gas adsorption at 77 Kelvin, which is the boiling point of liquid nitrogen. By measuring how much nitrogen adsorbs at different pressures, we create an adsorption isotherm. From this data, we can calculate the total surface area. The BET surface area equals the monolayer volume times Avogadro's number times the cross-sectional area of one gas molecule, all divided by the molar volume of the gas. Now let's discuss the practical applications of MOFs. Why do we care about these materials beyond their impressive surface areas? The first major application is gas storage. MOFs can store enormous amounts of gases like hydrogen, methane, and carbon dioxide. For example, MOFs are being developed to store hydrogen gas for fuel cell vehicles. The high surface area allows dense packing of hydrogen molecules. Storage capacity is expressed as the mass of gas stored divided by the mass of MOF times 100%. Some advanced MOFs can achieve 10 weight% hydrogen storage at cryogenic temperatures, meaning 10 grams of hydrogen per 100 grams of MOF. The second major application is carbon dioxide capture from industrial emissions or even directly from air. Certain MOFs can selectively adsorb carbon dioxide over nitrogen and oxygen, making them ideal for capturing emissions from power plants. Selectivity is defined as the amount of carbon dioxide adsorbed divided by the amount of nitrogen adsorbed. Values above 10 are considered good. The third application is catalysis. MOFs can act as catalysts or catalyst supports for chemical reactions. The high surface area provides an enormous number of active sites where chemical reactions can occur. Additionally, the pores can be functionalized with specific catalytic groups, creating highly selective and efficient catalysts. The fourth application is drug delivery. MOFs can encapsulate drug molecules in their pores and release them in a controlled manner. The fifth application is chemical sensing. MOFs can detect trace amounts of chemicals by changes in their optical or electrical properties upon adsorption. Let me give you an analogy that helps explain why MOFs are so special. Think of a MOF as an apartment building. Imagine a tall apartment building. Each apartment is like a pore in the MOF. The walls of the apartments are like the surface area where interactions happen. Now imagine replacing this apartment building with a solid brick of the same outer dimensions. The solid brick has almost no internal surface area, just the outer surface. But the apartment building has enormous internal surface area from all the walls of all the rooms. This is exactly what's happening in MOFs at the nanoscale. Each room in the building can host guests, just like each pore in a MOF can host gas molecules. The more rooms, the more guests you can accommodate. You might wonder, is there a theoretical limit to how high surface areas can go? Can we make even better MOFs? The theoretical maximum is constrained by the dimensions of atoms themselves. You can't make pores smaller than a few atoms wide. A rough estimate for maximum surface area is 1 divided by density times minimum pore diameter. As you reduce density and pore size, you increase surface area. Some ultra-low density MOFs are approaching theoretical limits with densities as low as 0.1 grams per cc. However, there are trade-offs. As you increase porosity and surface area, you decrease mechanical stability. The structure becomes more fragile. Despite their promise, MOFs face several challenges that researchers are working to overcome. First, many MOFs are sensitive to moisture. Water molecules can displace the organic linkers and cause the structure to collapse. Second, mechanical stability can be an issue, especially under the pressures needed for practical gas storage applications. Third, synthesizing MOFs at industrial scale remains challenging and expensive compared to traditional materials. Fourth, some MOFs have limited thermal stability and decompose at elevated temperatures, restricting their use in high-temperature applications. Let's talk about recent advances and where the field is heading. Researchers have developed water-stable MOFs using stronger metal ligand bonds and hydrophobic organic linkers. Mixed metal and mixed linker MOFs combine different components to create materials with tailored properties. MOF membranes are being developed for energy-efficient gas separation processes, potentially replacing energy-intensive distillation. Computational methods are accelerating MOF discovery by predicting properties before synthesis, saving time and resources. Let me give you one more thought experiment to really appreciate these surface areas. Imagine you could somehow unfold and flatten all the internal surface area of 1 gram of MOF material. You spread it out as a single atomic layer sheet, making it as thin as possible. This sheet would cover an area larger than a football field. All of that surface was compressed and folded into just 1 gram of material. This visualization shows the incredible compactness of MOFs. All this area, represented by the large rectangle, comes from this tiny cube representing 1 gram of material. Let's look at one more interesting mathematical aspect: how surface area scales with size. For a three-dimensional object, volume scales as the cube of the characteristic length L, but surface area scales as the square of the characteristic length. Therefore, the ratio of surface area to volume is proportional to 1 over L. As objects get smaller, this ratio increases dramatically. This is exactly why nanostructures like MOFs have such high surface-to-volume ratios. At the nanoscale, surface dominates over volume. Let me summarize the key concepts we've covered about MOFs. MOFs are crystalline porous materials built from metal nodes and organic linkers, achieving record-breaking specific surface areas. The surface areas can exceed 7,000 square meters per gram, equivalent to a football field in just 1 gram. This high surface area results from having nanoscale pores packed into a low-density framework. Applications span gas storage, carbon capture, catalysis, drug delivery, and sensing. Challenges remain in moisture stability, mechanical robustness, and cost-effective large-scale production. Despite challenges, MOFs represent an exciting frontier in materials science with potential to address critical energy and environmental challenges. Let me leave you with a final thought about the power of nanostructure. Nature has been exploiting high surface area structures for billions of years. Your lungs have an internal surface area of about 70 square meters compressed into your chest. Your intestines have enormous surface area from villi and microvilli to maximize nutrient absorption. MOFs are our engineered version of this natural efficiency, optimized at the molecular level for specific technological applications. We're learning to build structures like nature does, creating vast internal landscapes within tiny volumes, 1 nanopore at a time. This is the power and promise of metal organic frameworks.